Okay, this is an exciting video because you are going to start off. This is like one of the first, this is actually the first thing you're going to learn about vector calculus. Yeah, it sounds intimidating, but trust me, it's not as bad as it sounds. It's just there's a lot of theorems, and I will be making a video to sort all the theorems together to make sure that you guys know what all the formulas mean. Because I know a lot of calculus teachers don't like make formula sheets for your exams. So with that said, we're going to start off by doing line integrals of vector fields. And more specifically, we're going to be calculating the circulations. So, for my first point, okay, I need to look at my notes, hold up. For my first point, I'm just going to show you some general formulas, and I guess hopefully, I want to compress as much as possible because I know you guys have like TikTok attention spans. But, or maybe some of you do. I know I do. But let's say you have a vector field with two components, x and y, or dependent on two variables, x and y, not two components. And your vector field was, let's say, some example of some function, xy. Simplest, very, very simple vector field is the vector field that points directly outward in all directions. So let's see with this vector field, and you have some parameterization, some line that you want to calculate your circulation upon. And don't worry about the wording of circulation. Circulation is more specifically, you can use circulation to calculate work. But if you're just worried about the math, don't think of the word circulation as much. There's two ways you can calculate line integrals of vector fields. It's just circulation and flux. But I have separate videos on that, so you can separate that in your mind. But let's say you have a vector field, and you just dot it with your derivative of your parameterization. Okay, that's literally all. And maybe you have some curve, C. This is your meat and bones of your formula. That's the one you're going to be using. A more general run would just be vector field dotted with your tangent. With your tangent vector. But honestly, this one is right here is going to be significantly more useful, so we're just going to focus on that formula for now. It's the actual one that you're going to be using for your calculations. So what do I mean by this? Well, you're going to have some parameterization. I don't know, maybe you're going to have a straight line from 0, 0 to 1, 1 in the orientation given respectively, and I'll cover orientation in the next few problems because that's actually somewhat important in your parameterizations. But if you have 0, 0, 1, 1, your parameterization would probably be something like this, right? TT. And your bounds for t will be 0 and 1. All you're doing for this line integral is separating your components of your vector field. Let's say this is, let's change the color. Let's say this is P, and let's say this is Q, okay? Your first component of your vector field is P, your second component is Q. And you're just dot producting with your parameterization. So you're just doing a dot product with your parameterization with your vector field. So P dot your x parameterization of t plus Q times, not necessarily dotted, I guess, because it's more like times Q, your second component of your vector field, multiplied with your second component of your this is supposed to be a prime derivative of your x value of your parameterization. So I'm going to write this down. This is going to be the actual important one. But just a quick visualization of what you're actually calculating. This is not important whatsoever for your math. I guess it's very important for theory. Maybe math teachers may not like me for saying that, but I'm the student that got good grades on his exams by just worrying about how to do the math and not worrying about the proofs or the theories. So this is your line 1, 1, and let's say you have a vector field xy that just points out in all directions. Let's draw it with green. I don't know, something that looks like this, like this, I guess. I don't know. Just get smaller. something that looks like this. You're basically just calculating the, no, let's actually change the color. So this is your vector field, and let's say you have tangent vectors like in blue right here, given by your parameterization of R. So you're just dotting your green arrows with your blue arrows, and that calculates work. All right, if you've taken a mechanics physics class, you know that the dot product between force and displacement is going to be your work. For this first problem, your vector field is something simple. XY. Very normal, nothing too crazy. And hopefully your teachers will give you vector fields that are simple, because the whole point of calculus is to do calculus, not to do annoying arithmetic. So, you know, if your teachers are evil, they're going to make a heavy arithmetic and algebra-based questions, which I can definitely say are very annoying. So, what do we do? Well, first thing you do is parameterize. I was already getting ahead of myself. I wrote it down before I said anything. But this is my parameterization that I wrote down. And the reason why this makes sense is because your boundary for t can be some constants. So for t, the boundaries are just 0 and 1. Typically, you would want some constants, 0, 1, 0, 2. Something very easy to do, something with 0 in it, because 0 makes calculations a lot easier. But for this parameterization, the reason why this makes sense is because if you plug in your first boundary, you get 0, 0. And the output is your point 0, 0, which is the first point that we're referring to. And if you plug in 1 and 1 here, you get negative 1. Well, your point is 1, negative 1, which makes sense because that is our second point that we are parameterizing for. And remember, the orientation of this matters. And the reason being is because we are going from point 0, 0 to 1, negative 1. If you were going from point 1, negative 1 to 0, 0, your parameterization will look different. So your parameterization, if you wanted still the boundaries of 0 and 1 for t, it would look, let me solve this right now. It would look like 0, like 1 minus t, and 1, wait, t minus 1. Yeah. So this would be your, this is actually slanted right now. I don't know how to rotate this. Okay, I wrote slanted, but I don't know how to rotate this. And if you were to plug in 0, right? If you plug in 0, 0 into this, your first point would be 1, negative 1. Which makes sense with our first point. And if you were to plug in 1, 1, you would get 0, 0. So your parameterization will be different if you go in the opposite direction. So make sure when you're reading the problem, you parameterize right. So in conclusion, the order in which your points are organized, make sure to keep that in mind, especially when it mentions counterclockwise or clockwise orientation. But this is the right parameterization in context of this problem. So we're going to find the derivative of this next. Hence our derivative of our parameterization inside of our general formula here. And the derivative of this is just the derivative of all the components, which is 1, negative 1. Okay, now we have P and we have Q. Make sure these are parameterized. So our new vector field within our parameterization is just t negative 1. T and negative t, sorry. And we just dot our vector field with our derivative. And this is equal to the dot product between this guy and this guy. So all we do is multiply t with the first component, and we multiply negative t with the second component of our parameterization. So just their corresponding xy components. So when we do that, you get t times 1 plus negative t times negative 1, which is just equal to 2t. So our integral, when we set this up, remember our boundary is from 0 to 1 for our parameterization, so our boundary for our integral is 0 to 1, is just 2t dt. And the integral of this is something simple, it's just t squared. Our boundaries are 0 and 1. You plug in 1, you get 1. You plug in 0, you get 0. So our answer is just 1 for this problem. Okay, this one was a simple one, but for the next one, it's going to be a triangle, so prepare yourself for that. The first thing I'm going to do for this one, rather than finding the parameterization, is draw this out. So when I draw this out, it's just going to make it slightly easier for us to do our parameterizations in math. But first point is 0, 0, the origin. Second point is 1, 0. So we're going in this direction, left to right. And the third point is 0, 1, which is along the y-axis. And if we just connect back to the origin, looks like a triangle that is in a counterclockwise orientation because we're going, well, in the direction of my cursor, counterclockwise. Hence the arrows. So, first thing we do, well, how do you parameterize a triangle? You don't have to parameterize the entire thing, guys. All you have to do is parameterize just each line segment one by one and add it all together. So this is the hard part about line integrals of vector fields or vector line integrals. They're kind of annoying due to the fact that you have to you have to add all the things together. So we have to do 3 vector line integrals for this. Okay, let's start off. Well, the first parameterization is, let's start off with the one from 0 to 1, 0. So this parameterization is t 0. That makes sense given our boundary from 0 to 1. So our derivative for this parameterization is 1 and 0. So the derivative of t is just 1, derivative of 0 is just 0. And I don't know, if you want to try this out, you can plug in the numbers, but it looks pretty self-explanatory that 0 and 1 lead to this next point right here. So we're covering this guy right now. Once we have that, we have to, I don't know if I should erase this. I'm going to use this for the thumbnail, actually. I just take a screenshot of whatever has the most amount of words and then use that as the thumbnail. Which is, maybe I should make thumbnails so the click rate goes up. But for the videos. But let's go back to the question. So what you do here is parameterize your f boundary, or your vector field, sorry. So when you parameterize it, it's negative y. What's the y value here? It's just 0 in your parameterization. Make sure you don't pick your derivative to use as your substitutes. So 0 goes into here, so this is negative 0 or just 0. There's no negative 0. How about t? Well, your x value is just the x component of your parameterization, which is just t. So this is your new vector field. Okay, once we dot this, so we have to dot product your vector field with your parameterization, you get, and let's write this down. Let's actually write down the vector field. 0t dotted with your derivative, which is 1, 0 dt. You actually get, and your bounds are 1 and 0, because that's your bounds for t. You actually get, well, this just multiplies. Well, 0 times 1 is just 0. And t times 0 is just 0. So, all this just turns into 0. And then what do you do there? Well, your line integral is just simply 0. Just for this bottom line segment for now. So we have the first part of this. Let's make this smaller. We're the first part of this I guess, problem with this bottom line here. But we have to do the second part. And I'd like to do it in order. So the next thing we're going to do is parameterize this line right here. The line that I'm highlighting. So the slanted part of the triangle. And that parameterization looks something like so. You have 1 minus t, comma, t. And with our boundaries 0 and 1, this makes sense. If you plug in 0 here and 0 here, you get the point 1, 0, which is our first point down here. And if you plug in 1 and 1, you get 0, 1, which is the second point we want. Up top, right here, at the top of the triangle. And the orientation makes sense because that's the direction which our arrow points. From 0 to 1, it slowly makes this parameterization rise upward. Next, find the derivative of this. So when you find the derivative of this, you get negative 1 and 1. And when you parameterize your vector field, you get, since this is 1 minus 1, this is negative t. So this is negative t because that substitutes for y in our vector field. These are our y components. And x is just positive x, so we substitute for x. So this is our vector field here. If we were to write out our integral, the bounds are 0 to 1, as it is for t. And we're just dot producting our vector field with our derivative of the parameterization, which is negative 1, 1 dt. If you expand this dot product, you get, what is this? Negative t times negative 1 plus, let's put this in parentheses, 1 minus t times 1 dt. And if you solve for this integral, you just get 1. Okay, one last part. You have to solve for this part of your this part of the triangle for your vector line integral. So we have 0 and 1 so far, and we have to add them all up together at the end. Let's go ahead and do that once we figure this out right here. Oh, first parameterize, sorry. You know what? I'm going to separate this with a barrier. There you go. So it's not confusing. Maybe a better color would be for that. Let's use a, I don't know, let's use pink. I like pink. Okay. So, parameterization for the last line, going down. So remember, the direction matters. If you were to go from up, down, if you were to go up, or clockwise orientation, your parameterization would look like so. 0t. And your bounds would be from 0 to 1. But we're going downward. So if we want to keep our bounds of 0 and 1 for t, some very simple bounds, we need to change our parameterization. And that this new parameterization would look like so. 0 and 1t. This makes sense because if you plug in 0, 0, well, the first part is always 0. First component of this parameterization is always 0. But if you were to plug in 0, 0, you get 0, 1, which is the point up at the top of the triangle. And if you were to plug in 1, 1, you would get 0, 0. 1 minus 1 is 0. And that's the origin. And this orientation goes from 0, 1 to 0, 0, which is in line with our counterclockwise orientation. So make sure your orientation is always right. I probably said that so many times in this video. I don't know. If you want to count, just put it down in the comment section and tell me how many times I said it. But I have to repeat myself a lot because, you know, when you're first learning these things, it's hard to keep track of all the things that someone's feeding you information. So you have to repeat yourself a lot in order for, which is not a bad thing, in order for someone to, or you guys, for example, to actually retain the information in your mind. So the derivative of this is 0 and negative 1. And our parameterized vector field is negative y, sorry. Negative y is this guy right here. So we do negative y, which is just t minus 1. And x is just 0 here. So now we can set up our integral. 0, 1 as our boundaries, and we just dot product our vector field with our derivative of our parameterization, which is 0, negative 1. Turns out, if you simplify everything here, well, if you dot this, let's dot them all together actually to show you, you get 0 at the end. 0 multiplied by this is 0, 0 multiplied by this is 0, so your answer is 0 at the end. Therefore, our answer is 0 plus 1 plus 0. So the vector line integral for this problem was just equal to 1. Next problem. Okay, this problem looks like a word problem. Alright, looks like there's more words than numbers on the screen. But don't worry. For you math heads, okay, it's just a couple words that describe math. So, it's not that bad. And all jokes aside, reading is quite fun. I don't know. I 2 years ago, I didn't think I would say that, but if you pick the right book, it's kind of fun. Right now I'm reading a book called The God Particle, and it's about the Higgs boson. I don't know, you physicists out there that are learning Calculus 3. It's a pretty interesting particle. Quantum physics itself is pretty interesting too. But let's get into the video. So we have a semicircle with radius 1, bounded below with a counterclockwise orientation. See, it's not that bad. It's just a couple words that describe math. And this semicircle has a radius of 1, so let's draw it out. You know what? Fuck it. I'm just gonna use the straight line tool. Okay. Okay. Semicircle. Like this. Yeah, I drew that pretty decently. And the orientation is counterclockwise. So I'll draw like little arrows to show you what the orientation looks like. Has a radius of 1. Therefore, this point right here and this point right here are defined by the values of 1, 0 and negative 1, 0. So this is all we need. Well, our parameterization is simply a straight line along the x-axis and kind of a half circle. And maybe, as you remember, I don't know if you watched my last video for the scalar scalar function line integrals. You're not calculating circulation or flux or nothing like that. It's just something easier than this. But for that video, fuck, I lost track of what I was talking about. I'll just do the problem. Okay, parameterization. Maybe I'll start off with negative 1 to 0. So this parameterization, you can use something like 2t minus 1, 0, because there's no change in y. Or you can use, let's be more specific, with bound 0 to 1. Or you can use t minus 1, 0, with bounds 0 to 2. So what I mean by that, I can separate this to show you, but both your answers will still be the same as long as your parameterization makes sense in terms of this problem. Let's move this down lower. So I'll show you with our little boundary trick. So if you plug in 0, 0 here, you get the point. If you plug in 0 to here, it's just negative 1, 0, which is our first point that we're looking for. If you plug in 1, 1, you get 1 and 0, which is the second point we're looking for. And this is just a straight line. But how about if you plug in 0, 0 here, you still get the first point that's right. And it's the proper orientation too, because we're going from left to right here, or clockwise, counterclockwise, sorry. And if you plug in 2 and 2 here, you still get your point 1, 0. So 2 minus 1 is just 1. And this is always just going to be 0. So both ways work, but I'm just going to be using the boundary of 0, 1, because that's easier for integrals, or if you get some squared value. So the derivative of our parameterization is 2 and 0. Okay, now let's find the parameterized vector field. So our vector field is just negative xy. So negative x component of this is 1 minus 2t. So this is negative of this. So the negative of this is 1 minus 2t. And y is simply 0. So we have 0 here. And we can set up our integral by dotting our vector field. So remember, you dot your vector field with your parameterization, or you can use this guy right here. X prime is simply this guy right here, and y prime is simply this guy right here of your parameterization. But I'll just do it this way. So your vector field is 1 minus t, comma 0, dotted with your derivative 2, 0. And if you simplify this further, you get 2 minus 4t dt. And the derivative of this is simply, integral is simply 2t minus 2t squared. And our bounds are 0 and 1. If you plug in 1, you get 2 minus 2, which is just equal to 0. So the first part of our work or vector line integral calculation is equal to 0. Not so bad so far. Let's calculate the second part. So the second part, you're parameterizing I'm just trying to make space for our new thing. You are calculating a semicircle. So how do you do that? Well, let's separate our work first. Okay, I'm drawing slanted lines right now. Yeah, I give up. I'll just use this part. How do you parameterize a circle? Parameterization of a circle is, in a counterclockwise orientation, is cosine of t sine of t. And your boundary for this would be, let's make this smaller so I can write the boundary on the other side, right here. Your boundary for this, for t, would be from 0 to pi. Because pi marks, I guess, when you hit the other side of the x-axis for your circle. Let's see if this makes sense. If you plug in 0, 0 for this, you get the point 1, 0, which is our starting point. That makes sense, going in a counterclockwise orientation. And if you plug in pi, you get 0 and negative, sorry, not 0, negative 1. You get negative 1, 0. So that makes sense. Hit the other side, which is the other point that we're looking for. And if you were to plug in, I don't know, pi over 2, some number between, you would get, here. You would get this point up here, which is just 0, 1, if you wanted to test that out for yourself. But we're going to keep solving this problem. Our derivative is negative sine of t, cosine of t. And our parameterized vector field is, so negative x, we get negative cosine here, and y, which is sine of t. And if we dot product this, you get negative cosine t, comma, sine t, dotted with your derivative, negative sine t, cosine t, dt. From 0 to pi, you get 2 sine t cosine t. So if you simplify everything, you just get this dt. And the integral of this is just sine squared of t from 0 to pi. And all that just equals 0. So in the end, you just got 0 anyways. And trust me, not all answers are going to be 0, but I guess for the specific problems I gave you, they're 0. So 0 plus 0 is just another big fat 0. that's the answer for this problem. So if you have any questions, put it down in the comment section. Hope you all have a great day. Summer break has just started for me, so I'm having a great day.